All right, strap in, everyone, because today we're going headfirst into Einstein's theory of relativity.
It's a big one.
It really is. We're talking about a theory that revolutionized how we think about the universe itself.
And we've got a fantastic guide for this deep dive. An essay by Jörg-Owe.
The theory of relativity simply explained, right?
It's the one.
We'll try to do it justice.
Feels good.
So, I know a lot of our listeners are probably familiar with the basics, but even so, relativity has a reputation for being, well, pretty complicated.
Oh, absolutely.
And that's where we come in, right?
Definitely.
We're going to break it down into pieces, make it understandable.
And fun, hopefully.
Exactly. And the cool thing is, relativity isn't just about, like, black holes and distant galaxies.
No, not at all.
It affects things right here on Earth, too, even if we don't realize it.
Our everyday lives.
Exactly. So, I guess the first question is, where do we even begin?
Well, before we get to Einstein, we need to set the stage right.
Okay, I'm following.
So how did people think about space and time before Einstein came along?
Well, I guess they thought of them as completely separate things.
Right.
Like space is just this empty stage, and time just marches on.
Exactly. Unchanging, absolute, just like a cosmic clock ticking away.
It all sounds very straightforward.
It was the Newtonian view, Sir Isaac Newton's world.
Ah, got it.
And that worked pretty well for a long time, but then... Well, by the late 1800s, early 1900s, things started getting a little shaky.
What do you mean?
Well, scientists like Albert Michelson and Hendrik Lorentz, they were doing some experiments, and the results they got just didn't fit with the old Newtonian way of thinking.
Kind of like trying to jam a square peg into a round hole.
Yeah. Schneepak compares it to finding a puzzle piece that just won't fit no matter how hard you try.
So enter Einstein.
Right. He comes in and says, hey, maybe we're looking at the puzzle all wrong.
Yeah, gotta think outside the box.
Exactly. And he uses those inconsistencies, those misfits, to build his own theories.
His theories of relativity.
You got it.
Now, Schneepak focuses on two main parts, right? Special relativity and general relativity.
Exactly.
And I think it makes sense to start with the special one, right?
Yeah, let's tackle that first.
So what is special relativity? In a nutshell, I mean...
It's all about frames of reference.
Frames of reference.
Like, imagine you're on a moving train, and you toss a ball straight up in the air.
Okay, I'm picturing it.
To you, on the train, the ball just goes up and down.
Yeah.
But to someone standing on the platform watching the train go by, the ball is also moving horizontally with the train.
Ah, yeah, because they're seeing it from a different perspective.
Exactly. It's all relative to your frame of reference.
Okay, that makes sense.
Now, here's the kicker. Special relativity says the laws of physics are the same for everyone as long as they're moving at a constant speed.
Okay.
But there's a big but.
I was wondering when the but was coming.
The speed of light is constant.
Constant.
For everyone, no matter how fast they're moving.
Well, wait a minute. Hold on. So you're saying that, like, if I was on a spaceship traveling at, I don't know, half the speed of light, and I shined a flashlight forward, that light from my flashlight would still be traveling at the speed of light. Not 1.5 times the speed of light.
Exactly.
But how? How is that even possible?
That's the mind-blowing part, right? For that to be true, for the speed of light to always be the same, our ideas about space and time have to change.
You mean they can't be absolute?
They have to be. Relative?
Relative, like they can bend and stretch and change?
That's where things start to get really interesting, yeah.
Okay, now my brain is starting to hurt a little, but I'm hooked. We've got to take a break, but when we come back, we're going even deeper into this rabbit hole, and we'll unpack what this relativity of space and time actually means. Don't go anywhere. Welcome back, everybody. So we left off talking about how space and time are not these rigid, unchanging things.
Right, exactly.
And I think a lot of people, myself included, would say, well, hold on, how is that possible?
It's a big shift from the way we usually think about the world, yeah.
It is. So can you help us understand what this relativity of space and time actually means?
Sure, and to do that, we need to bring in the big kahuna.
The big kahuna.
Gravity. That's where general relativity comes in, which Einstein published in 1915.
Ah, so this is where it all comes together.
Yep. General relativity basically says that gravity isn't a force.
Wait, what? Hold on. If gravity isn't a force, then what is it?
Well, Einstein said that gravity is actually a curvature of space-time itself.
A curvature? Like space-time is bent.
Exactly.
Oh.
Think of it like a bowling ball on a trampoline.
Okay, I'm picturing it.
The bowling ball creates a dip, right? a curvature in the trampoline surface.
Yeah.
Now, if you roll a marble across the trampoline, it's not going to travel in a straight line, is it?
No, it'll curve around the bowling ball.
Right, because the trampoline itself is curved.
So in this analogy, the bowling ball is like...
A massive object like a planet or a star.
And the marble is like...
A smaller object or even a beam of light.
So gravity isn't a force pulling things down, but rather objects are just following these curves in space-time.
Exactly.
Wow, that's pretty mind-blowing.
It is, and leads to some really interesting consequences.
Like what?
Well, remember how in special relativity, time slows down for objects moving at high speeds?
Yeah, the whole twin paradox thing.
Right. Well, general relativity says that gravity itself can also affect time.
What? Gravity can slow down time?
Yep. The stronger the gravitational field, the slower time runs.
So, like, time runs slower at the bottom of a mountain than at the top?
Technically, yes.
Wow, so my feet are actually younger than my head.
Well, the effect is tiny here on Earth, but it's measurable, yeah.
I mean, it's still amazing to think about.
It is, and it's not just a theoretical thing either.
Yeah.
Like GPS satellites, they have to take this into account. Really,
Okay.
because they're orbiting Earth in a weaker gravitational field.
So their clocks run a little faster than clocks on the ground.
Right. If we didn't correct for that, GPS wouldn't be accurate at all.
So my phone's GPS is basically relying on Einstein's theory of relativity to work. That's crazy.
It is. It shows that relativity isn't just this abstract theory. It has very real-world applications.
And speaking of mind-blowing, there's one more thing we have to talk about.
I know what you're going to say.
EMC summy.
The most famous equation in physics, probably.
Even
Yeah.
people who know nothing about science have heard of that one.
Yeah.
But what does it actually mean?
Well, Schneppat explains that it describes what's called mass-energy equivalence.
Mass energy equivalence.
It means that mass and energy are basically the same thing, just in different forms.
Wait, hold on. So you're saying, like, my coffee mug has energy stored inside of it.
Yep. It's like mass is frozen energy and energy is melted mass.
So the equation tells us how much energy is contained within a given amount of mass.
Exactly. And c, that's the speed of light squared, which is a huge E number.
So even a tiny amount of mass contains a lot of energy.
Right. That's the principle behind nuclear power, for instance.
Because nuclear reactions convert a small amount of mass into a massive amount of energy.
Exactly. And it highlights how impactful relativity is, not just for understanding the universe, but for technology, energy, all sorts of things.
It's really incredible when you think about it.
It is. And it's not just the science itself that's fascinating, but also how these theories were received by the public.
Yeah, I'm curious about that. I mean, this is pretty complex stuff. Did people even understand it back then?
Well, that's where things get really interesting, and that's what we'll explore after the break.
We're back and ready to wrap up our deep dive into relativity.
And we're talking about how the public reacted to these mind-blowing ideas.
Yeah, I mean, it's one thing for scientists to debate this stuff.
Right.
But how did everyday people wrap their heads around, like, warped space-time and time dilation? Did they even try?
Well, it might surprise you, but Einstein and his theories became quite the sensation.
Really? Like pop culture famous?
Oh, yeah.
But how? Did everyone suddenly become physics experts?
Not quite. But Jörg-Owe Schneppat points out something interesting in his essay.
Okay, what's that?
He talks about how back then, newspapers were the main way people got their news.
Makes sense. No internet or anything.
Right. And newspapers, well, they love a good story.
Especially a sensational one.
Exactly. And what's more sensational than a theory that completely upends our understanding of the universe?
So Einstein's theories were perfect front page material.
You got it.
Headlines about warped space and time. It must have been wild.
Oh, it was. And it wasn't just newspapers. There were newsreels, too, showing actual footage of Einstein.
I can picture it. The frizzy hair, the thoughtful look.
Yep. He became this global icon, a symbol of genius.
Imagine that, being famous for your brain.
It's pretty remarkable.
It is. It is. But Schneppat mentions that Einstein himself wasn't always thrilled with the attention.
Yeah, he called it dazzling misery at one point.
Oof, I can see how it could be overwhelming.
All those requests for interviews and appearances, it can be a lot.
Even for a brilliant scientist, yeah.
Definitely. But all this publicity, it wasn't all bad, of course.
Oh.
It sparked a huge public interest in science.
So relativity wasn't just confined to, like, university classrooms.
Oh, not at all. People were discussing it in cafes, at dinner parties.
Wow, that's amazing.
It was a real cultural moment. And it wasn't just, everyday folks who got caught up in it.
Whoa.
Artists, writers, musicians. They were all inspired by Einstein's ideas.
So relativity started showing up in paintings and novels and symphonies.
Exactly. It became this symbol of the changing times, The old ways of thinking were being challenged, new perspectives were emerging.
It's fascinating how a scientific theory can have such a widespread cultural impact.
It really is.
And it's not just a historical thing either.
Right.
Scientists are still exploring the implications of relativity today.
Oh, absolutely. Cosmology, quantum mechanics, the search for a unified theory of everything, it's all connected.
It's a testament to Einstein's genius that his work is still so relevant so many years later.
Definitely. And I think what Jörg-Owe does so well in his essay is show that relativity isn't just this abstract, incomprehensible thing.
Yeah.
It has real-world consequences, and it shaped how we understand the universe and even ourselves.
Absolutely. So the next time you use your GPS or you look up at the stars, take a moment to appreciate the power of Einstein's ideas.
I like that.
Those ideas that once seemed so radical, so out there, are now woven into the fabric of our lives and our understanding of the cosmos.
It's a beautiful thing.
It really is. And on that note, I think it's time to wrap up this deep dive. Big thanks to Jörg-Owe for providing such a fascinating and accessible exploration of a truly mind-bending topic.
Absolutely.
And to all of you listening, keep exploring, keep questioning, and never stop being curious about the universe and our place within it.